Welcome back to the second part for section 2.7. And we were just discussing our best measures of central tendency and dispersion after we learned about the normal curve. And there are a couple of ways that we can decide this. So we can use our graph and numerically. So if our graph is symmetric, then our mean and our median will be approximately equal. And if that is so, then our best measure of center that we're going to use moving forward to represent our data would be the mean, and the standard deviation would be our choice for the best measure of spread. If our data is skewed in either way, then we're going to use the median and the IQR. And if the mean is less than the median, and that's where you have to make that decision, how much less is less. If the mean is less than the median, then the data is skewed left. And that will look something like this. It'll be really kind of thin out here. Now, if the data is skewed right, it will look something like this. Well, the tail will be out to the right because the mean is greater than the median. And remember, whichever way that inequality is pointing is where it's skewed. And we always do the mean on the left and the median on the right so that we have a consistent comparison. So next up, you have a little example that you're going to turn off and go and answer in Canvas. It says, let's say two students, Amy is in algebra class and Betsy's in statistics. Amy is very happy with her score of 70% on her exam, while Betsy is discouraged with her 80% on her exam in statistics. Why would Amy with a lower score be more encouraged than Betsy with a higher score? So make sure you turn this off and go and answer that question in the form in Canvas, and then come back and we're going to check out the next topic that will build on this concept. So Amy and Betsy, let's look at why they might feel differently about their scores in two different classes. So the z-score. The z-score is the average number of standard deviations an observation is either above or below the mean. We can use a z-score, which is the number of standard deviations of values away from the mean, to use as a comparison. It's basically to compare things apples to apples. So the z-score is taking your value minus the mean divided by the standard deviation. Okay, so this is going to look like x minus x bar over s if we have population data. I'm sorry, if we have sample data. I apologize about that. And then it will look like x minus mu divided by sigma if we have population data. So it's the same formula. It's just the symbols will look a little bit different, but it's always going to be your value subtracting the mean. And if it's negative, it means that your value is under the mean. And if it's positive, it means your value is over the mean. So throughout this chapter, we've been talking about visually finding unusual observations that we call outliers. And then we also learned how to use a box plot and the upper and lower fence to find outliers. And now we're going to use the idea of the standard deviations. So earlier in this particular lesson, we said that any observation that is above or below the mean by 2 standard deviations is considered unusual. And that means our z-score. So if you are above your mean by 2 standard deviations, your z-score is going to be 2, because that's what a z-score is, the average number of standard deviations you are above or below the mean. If your z-score is less than or equal to a -2, then you're also considered an outlier. Okay, so these are the 2 ways you're going to be considered an outlier. So let's look at example 7. It says 2 students, John and Allie, from different high schools, wanted to find out who had the highest GPA when compared to his school. Which student had the highest GPA when compared to his school? Question mark. Hint, I'm saying find the z-scores of both students. So John and Ali had different GPAs, and at Ali's school, his goes on a different scaling. His goes on the 100% scaling in his school, and John's goes by the 4-point scaling that most schools use. So let's look at John's Z-score. So it's going to be his GPA, subtracting the average at his school, divided by the standard deviation. And we're going to find that. Which is a negative 0.15. So the negative tells us that his GPA is under the average from the school, which is true. And his Z-score is a negative 0.214. Then we're going to look at Ali. Ali has 77. Subtracting 80 divided by 10. He is actually scoring lower than his school average as well. So if we look at this on a number line, and here is 0, here is a negative 0.5, here's a negative 1. John is right about here, and Ali is just past John here. So it looks like John is slightly higher. He's closer to 0. Compared to the other students at his school. Let's look at another. Example 8 says, 2 swimmers, Angie and Beth, from different teams, wanted to find out who had the fastest time for the 50-meter freestyle when compared to her team. Which swimmer had the fastest time when compared to her team? So if we look back at the high school score, a higher score is a better score, right? When we're talking about GPA, we want something higher. So when we talk about swimming and speed, we want something lower. So that's also something to take into account. So to be able to compare them, we need to compare them by their Z-scores. And that's because we want to put them in comparison of apples to apples. We want to compare Angie to her team average and standard deviation. And we want to compare Beth to her team average and standard deviation. So Angie is 26.2, subtracting 27.2. divided by 0.8. And we can see that Angie is definitely faster than her team's average because she's underneath that. So she is 1.25 standard deviations below the team average. And then let's look at Beth. Beth is also faster than her team average. And she's faster by more seconds, right? She's under her team average by 2.8 seconds, where Angie was only by 1 second. But Angie's team has a smaller standard deviation. They're closer together than Beth's team. So let's divide this. And it looks like Beth is under her team's average by 2 standard deviations. So we're going to say that Beth is faster compared to her team. Okay. The last example for chapter 2 is kind of a culmination of things that we've done in chapter 2 and putting it all together. So it says the table below gives the percent of children under the age of 5 considered to be underweight in 130 countries across the world. This is the most recent data. So I put them in groups because whenever you have a really large data set, which we do, instead of typing them all out, sometimes it's easier to get a bigger picture by putting them into classes. And we did that with our histograms, and we did that in chapter 1.3. And so I did that here for us to be able to get some practice with a weighted mean. So to use classes effectively to find the average percent of children in countries across the world that are underweight, I would have to get midpoints for each of these classes. And so I wanted to go over again how to find midpoints. So midpoints are taking the lower bound plus next lower bound and dividing by 2. So the first one is going to be 0 plus 10 divided by 2 is going to be 5. And then the next one is going to be 10 plus 20 divided by 2 is 30 divided by 2, which is 15. So let's go ahead and put those up here. Now, if you can see that you have a consistent width, we can see that we have a consistent width of 10. 0 to 10 is 10, 10 to 20 is 10, 20 to 30 is 10. Then your midpoint should also go increase by 10 because you can see that our upper bounds also increase by 10. They will be consistent. Sometimes you get data where the tables that are given to you are not consistent in their width. The goal is that they are, but they're not always that. So we should have 5, 15, 25, and 35. Now, doing a weighted average in Desmos can be done, but also it's easy to do it in Microsoft Sheets, Microsoft Excel or Google Sheets. So I'm going to share my screen and show you just a couple of ways we can look at this data. I wanted to show you in Excel, Microsoft Sheets, where I put the data in here and my midpoints, and I looked at this in a using my midpoints here, and I used a histogram. Now, histograms are not easily made with grouped data in Desmos. You have to have raw data in Desmos to make histograms. So I can only make them in the width of the classes. So my classes are a width of 10, so that's the width that I had to use here, unless I broke it down further, which I did, but we'll talk about that in a minute. So if we go to Desmos here, in Desmos, here, I put my data in here so I could find the mean. So here is my weighted or my midpoints and my numbers of countries. And then I'm going to take the total of X1 times Y1 to get my weighted there, because there's 72 countries that had a midpoint of 5% of undernourished children. And then I'm going to divide by my Y1s because that's my total number of countries. So it looks like on average, 11.38%. On average, countries have 11.38% of children undernourished. So let's go and write that down so we can see what that looks like written out. We want to describe that accurately. So on average, countries around the world have approximately, APPROX, approximately 11.38% 38% underweight. Children. So are there any intervals of data that seem to be unusual? And it looks like our data is skewed right. So it it looks like they're skewed right. So it looks like maybe the 30 to 39%. Possibly it's definitely skewed right. And so Yemen has the highest proportion of children under 5 years of age who are underweight. Does Yemen have an unusually high proportion of underweight children compared to other countries? So let's go check it out.